ARM microcontroller and embedded system module 4 session 5. So today we will discuss two languages used for designing the firmware. Assembly level language to begin with. So assembly level languages so far, if I'm not wrong, you had 8086 and even this semester you're having ARM. So both languages to some extent you're familiar with, in which we will be using mnemonics, and from mnemonics, each mnemonic example you can take it as for Cortex M3 you can take LDR, load directly the data into a register. LDR mnemonic has its own hex code or binary code with it, and as soon as you invoke this mnemonic, its equivalent hex code will be used, and using this hex code the processor or the controller will understand what basically that instruction is. So it is here 32-bit, and some instructions are 16-bit because we are using thumb 2 flavor. Okay, so the procedure what we follow here for designing a firmware, we are supposed to use either a text editor we can follow, or we can use a WordPad and we write a program in it. And since we are making use of assembly level language, you can use a tool for ARM Cortex. You can use a tool named as GNU ARM Embedded Toolchain, or simply you remember ARM compiler toolchain. So this ARM compiler toolchain is having the compiler, assembler, linker and loader, all methods or all programs required for getting your executable file which you are going to finally dump onto your machine. All programs are existing in this toolchain. Just remember, it is a ARM compiler toolchain. Toolchain in the sense set of tools you're having. Set of tools includes assembler, compiler, Y compiler. Over here we often call it as a cross compiler rather than the compiler. So cross compiler because we are using .c file too. So if you would have used just assembly code .asm file or .s file, then it would have been just assembler. Since we are using both languages it should support your ARM target machine. Hence we need to use a more sophisticated program which should include compiler as well as assembler. Fine, so we write a code first, then we will be using a tool chain, a huge program which has all the methods for converting a given assembly level language into a machine level language. Now this talks about the flow structure, how you're gonna get a executable file which you're going to place it on your machine. So you have a source file which we normally call it as a .asm file. Then here comes your module assembler. We call this as a module assembler because this is gonna assemble only one module, one single module. So far, if I'm not wrong, two assembly level programs we have executed in part A. One happens to be finding the sum of 10 numbers, and one more will be multiplying two 16-bit numbers. So both program we had only one file, so you can think as if that's your source file, one source file you had. You were not having a second source file. So module assembler would give you its equivalent object file for a particular module, and we require this library now because there are some symbols which are not resolved. For example, when you're talking about this .asm file, there are assembler directives which would talk about which region your code begins with, and also the data type of your variable which you're using. All are addressed in the assembler directives. It directs the assembler that is this variable has to go to which region, this program has to go to which region. For example, assembler directive happens to be area, assembler directive happens to be DCD, assembler directive happens to be DCB. So what does DCD do? DCD define constant data. So this creates a space for your data with 32 bits because we are using 32-bit system. So there are this labels or this symbols. Assembler directive needs to be converted, or it should be understood. to make it understand, you will be using this library file. So in this library file, all assembler directives definitions are addressed. Suppose if you are using DCD, how many number of bits should be assigned for a data, that is addressed in this library files. And also this library file includes the startup file, that is to run the program as soon as you press reset, how the sequence of the program, how it should run, that is addressed. So startup file will be executed, and that startup file is gonna call the main program wherein you write this piece of code. And finally, once the program is completed, it terminating program is also addressed in it. So this library right now, since you're having only one program, would it creates one object file, and this object file and this library, using this two are passed on to a linker. So linker job is here to give you the uh, object address. Now this object you have, and this is also having a address, so you will create a address, code region and data region, and it will be stored respectively. But since you're using this library information also, this library converted data would also be, you should provide a memory for this library also. So the job of the linker over here is to, before loading it into a physical memory of your microcontroller, provide the address for your data segment region, code segment region, and also if at all you including any library files in this module, give that address to. So finally, this absolute object file, with the help of a linker program takes many files, and it is used for linking. So in case if some of the methods are not defined in one object, and if it's been used, for example, you think as if one more example we will consider, wherein assume two files are there, two ASM files, and this second file, uh, you're saying that include this second file in first file. Okay, so suppose you try say that include, but here if it's not meant for exporting, then you will get a unresolved symbol error. Assume you are referring one function belonging to this module, and here you have to explicitly specify that the function which you're gonna export, you're going to export this function, it has to be addressed. If you don't say that you're exporting, then definitely you'll get a unresolved symbol with the help of a linker. It says that there is a symbol which is referred in this module 1, but it is not exported. It is not in the export mode. Here you are importing it, but here in this it is not addressed as export, so you get a unresolved symbol scenario. Okay, we will see how what is export and what is import mode. So once you get object file, then you have one more program which is in turn to convert a object file into a hex file. Okay, so this is about the source file to object file translation. One simple example we will have a look at what basically I was talking about. This was your .asm file. Here what we have done is we had created one function which will be called, the function is called by the main program. That's what you're going to do, and it is going to print the message hello. Okay, so this is your ASM file. You're familiar with this. As soon as the assembler assembles this code, this piece of object, so you're gonna get an object file for example.asm. You're gonna get two files. This is your example.list file. This example.list file, when you observe properly, this gives you the details about the address as well as the content, mnemonic, where this mnemonic is located in which address. So all this information which was not there when you look at your original source code, you can find it in this object file. Okay, and this object file .o object file would provide you some message like assembling, all those information content will be there in this object file. So remember, whenever you compile, whenever you assemble, you're gonna get these two files. Now using your linker, this definitely this module you have to link. Along with this, there is a startup file which gets also linked together. So if you look at the final absolute object file, it is, this is your map file for your final object file. So you can observe, uh, so this is data segment stored for reset sequence. Reset is actually the first program which gets run. Along with that, you have a code segment for a code segment, this region 2 and region 1. Basically, this is your program. This 2 location indicates the data segment which we have used. This was your program, had two segments, data segment and a code segment. So when you observe this map file, here it is addressed the total number of size consumed by your code and total number of size consumed by your data. Okay, along with that, startup file, which is this is actually your startup file. Even this you are supposed to use. So all are having a different address, and this address cannot be relocated. You cannot try to modify this address, and the same address is going to get into the into the memory of your IC. So that's the job of a linker. Okay, and these are actually the comments which, like, you look at this .axf file. This is your absolute object file. Two, you have this, you call it as .axf file. When you pass this file onto a object converter, object to hex converter, you are going to get the final output, which is your hex file, which looks like this. This is your pure binary code, given by uh, object to hex converter. Okay, so you can just have a look at, because already you are having a compiler. You can just write a simple program and try to compile it using a build option. Just figure out how many files gets loaded, and how you can analyze the structure of this. Okay, now let's move back to this section. This is actually the explanation of linker as addressed. This was one object, this was second object. A linker will link these two objects together, and you're going to get a merged object. And this merged object, you can consider this is the code segment. This is the data segment area for object 1, and this is a code segment area for object 2, data segment area for object 2. So linker would ensure that when you get a final object file, two data segments are merged together, and two text segments are also merged together. You do not have to worry about this .bss file. This is uninitialized segment which we will be initializing, so it will go to uninitialized region in the final memory ROM. Okay, so BSS, don't worry, because this is for Texas Instrument DSP processor. Its linker looks something like this. Okay, so here this code region was addressed as this for your Cortex machine. This is not your code area, it starts from the beginning. Okay, so there, this ultimate text file including this two objects code region goes to this place. Then this two merged data region goes to the data segment, which is this region, data segment initialized. This is initialized data segment. Okay, so this is how your assembly code and translation works. Okay, now let's discuss few commands like public and external. Suppose, assume when you're trying to build, when you press build command using a simulator, assume there are three functions, and here the public keyword, if public keyword is used followed by that you're using a function, then you're saying that that function is going can be exported. I repeat, you use a public keyword followed by function. If you're defining, then it means that the function can be exported to some other modules. Suppose in a module, if you're defining external followed by that you use a function name, then you're saying that you're going to import it. Okay, this public and this extern keywords are meant for 8051 programming language. Okay, similarly for ARM Cortex, public is replaced by export and extern is replaced by import. Suppose, if you are not wrong, you might have observed this in the main program .asm file, we always use export main, and in the startup file somewhere down the line 250 or 260 line, there is a command import main. So that startup file is going to include this function or import this function which is addressed as export. Okay, so this is one example wherein the scenario is you have put character, two functions put character, and both are saying that public, which means you can export this function to some other function. So here assume this module is going to grab this put character. Since you have two public definitions, multiple functions you have, and the linker right now, when it is trying to link all these three files together, then it is going to provide a error message saying that which among these two functions, which put char method to be picked, because both are meant for exporting, and here you are importing one. Which one from these two you are supposed to import, that linker will not come to know. Hence it will provide a message, error message, while linking multiple public definitions. You have a multiple public definitions, so unable to resolve this, so you have a resolve error. Okay, this is one thing, one scenario what why linker error you will get. And this is one more scenario. In this case you have defined, you are using a function known as put carriage return line feed. That's a function, put carriage return and line feed. It has to be imported any from either from this method or this method. So here you have that method, but you have not addressed it as external. Okay, I repeat, you have not mentioned it as, sorry, public. It should be mentioned as public, then only you can export. Okay, since it is not mentioned as public, so this one, even if you have addressed it properly, so you'll get a unresolved external symbol put character, because this put carriage return and line field is not meant to be exported in this. So this is you don't have a keyword written as export, hence you get a problem here. Okay, so export is nothing but public. Fine. Then we have a library file creation and usage. We can try to create our own library. You have a facility for that. We will try this since in part B few experiments we have already covered. We will try to explain hex key keyboard experiment, wherein we will be using LCD module there, but LCD module program already it was explained. Hence what we will do is for hex key, we will create a library, and we will put all the essential configuration methods, initialization method, command, data for LCD, to enable LCD, everything we will put it under a file, and we will include that file into our hex key, so that the size of your hex keypad interfacing program becomes shorter. So we will see how it can be done in later stage. So this facility you have, so this facility is mainly used, say that user, if he wants to create any library, he can do it, and later the created library can be used by a third party users can just use that module or library, so that he doesn't have to worry about the exact methodology, how exactly each hardware works, which pins you will be using, all those he do not have to worry about it. So you have to do work for others, and they will just use your library, and they will build their application. Similarly, you have a linker and locator. This for your key for 8051 platform microcontroller, it is for microcontroller platform, library file is having this extension, and linker, and also the object to hex filer program name is BL51. So this is actually a program which is used for linking, and for object to hex file function, OH51 is a program, a small software belonging to the keel, which is used for converting object to hex file. Okay, so that's what you have for assembly code instruction. I'll discuss the advantage of assembly level language based development. So assembly level language based development, one thing what you can observe is it is efficient code memory and data memory usage. uh, so why would you say efficient code memory and data memory usage? Assume that you write a piece of code in assembly code and you write its equivalent C code. While you observe, for you, uh, as you are familiar with C, you might think C is actually the best program over here because it consumes less line. So you have a application written using assembly code, and if it takes 20 lines, in C, if it takes 4 lines, you might think that this 4-line code is actually the optimal code with respect to assembly code, which is having 20 line of code. But the what happens when you compile using a cross compiler, when you convert .c file into a machine file, intermediately it gets converted to assembly code, and when you observe that assembly code, that would have 100 lines, just 4-line code you had, and it will be converted into 100-line code with many of the functions will be set to no operation. So this is not your optimized code. So you can write optimized code provided you're very good in processor dependent instruction set. So if you know well in advance the instruction set of your ARM Cortex 3, then you do not have to worry. You do not have to go in C background, and you do not have to work in C background. You can directly use assembly code piece of line itself. So it will be very much optimal, and performance wise also it will be effective because assembly code is very much closer to machine code. Rather than C to assembly you need to convert, then back from assembly again you need to convert it into machine level language. And one more advantage of your assembly code is low level hardware access. So assume that you have a hardware, a separate hardware, a network vectored interrupt controller, which is extra hardware in your Cortex M3 controller. And this the job of this controller, network vector interrupt controller, is to ensure that when you have multiple interrupts, handle it based on the priority set. So for addressing the priority, you have a interrupt enable register, which wherein you can define the priorities too, and also enabling whether the interrupt or disabling the interrupt can also be addressed in this register. And this registers, which is basically for a Cortex M3 machine, could be addressed easily using assembly code. Rather, if you try to program it using C code, embedded C code, it might take huge number of lines to execute. Sometimes it may not be possible to implement at all. Hence, some low level hardware access would be efficiently covered or efficiently dealt or efficiently served with the help of your assembly code. Finally, code reverse engineering. So this is reverse engineering is a concept wherein from your hex file, that is from the converted hex file, using deassembler is a program which would be used for which is used for analyzing your mnemonics from the hex file. So you can run the deassemble code, you can pass the input to the deassemble code, and you can visualize what are the mnemonics. Using this mnemonics, you can change this mnemonics, and also you can do the reverse engineering in this case. So that's the reverse engineering, and you can directly change the firmware whenever you require, but it requires intelligence too. Okay. And some of the disadvantage of developing firmware using assembly code happens to be high development time. Definitely it requires a lot of time. Reason why we say lot of time, because you should understand the architecture of the controller first for developing this language, and also writing assembly code is not that easy. Since instruction set you should be familiar with, it can be optimized, so it requires more time to develop this product into the market if you are using a firmware developed using assembly code. And developer dependency, you have to depend always on the developer, the person who has developed the firmware. You have to always be in touch with them to understand, or to, in case if something goes wrong, he can correct it. Okay, so that's one more thing, you have to depend on the developer. And non-portable, non-portable in the sense, suppose if you're using a program, if the firmware is written in your ARM Cortex M3 instruction set, then at any cost this code cannot be run on some other ARM platforms. Like ARM 7 cannot read this instruction which are based on Cortex M3 set, because it uses thumb 2. So you get a issue. So it is not portable. One program instruction set cannot be used in another program or another processor dependent language environment. Okay. So this is about assembly code. Next we will look at high level language based development. Here firmwares are designed with the help of a high level language. So popular high level language which we use for designing the firmware happens to be a C, C++, or even Java could be made used. But more frequently we use for developing firmware, we use C, embedded C. That's the platform which we will be using extensively for writing the firmwares. And in this case, the steps involved for developing or designing your firmware using C code: first you write a C code using a notepad or a text editor, and enters the extension of this .c file. Then you can use the supported compilers, cross compilers you can use. For example, if if you're using key software, you for 8051 microcontroller, if you want to use a build firmware using C code, then C51 is your popular cross compiler which is used. Whereas for the ARM Cortex, as addressed, ARM compiler tool chain does everything that has a cross compiler along with. Okay, so cross compiler is a program basically which is going to take .c file and it is gonna give you a hex file in turn. Okay, so the cross compilers for different high level languages for the same target processor would be different. Okay, high level language is a different high level language for the same target processor or different. So there are keel based, there are embed based compilers. So you have different compilers for the same target machine, and it functions differently. Okay, so this is your block diagram of the high level language to machine level language conversion. So what you have here, you have a .cpp file or .c file. So here only one difference you have: rather than using module assembler, we will be using module cross compiler. So this program does the task of converting a .c file into a .object file. Once you're gonna get the .object file out of it, then again the procedure is same. You use a linker. So the reason why we use linker is to resolve some of the labels which you have written in your .c file. For example, assume you are including a library for writing part B experiments. You have used lpc 17x6.h header file. So that header file is having the core instruction set of your Cortex M3 machine. So all are actually the library files. So this would be resolved when you're trying to link, because anyway we are supposed to use this device dot header file that has a huge amount of instructions addressing your Cortex M3 machine, and whichever instructions are you're using. For example, for developing stepper motor, you might have been used LPC GPIO1, LPC FIO directional flag, LPC FIO pin flag. Those are defined in this device LPC 17x65. So this is the library which you'll be using, which has the definition which port you are using, what is the bit size, what is the data type. So once you give it to a linker along with that, so it is going to give you again a final absolute object find with address for all the objects whichever you are using, and also for some of the routines available in the library. So after this you use a object to hex file converter and you get the hex file out of it. So this could be dumped onto the machine. So this for a programmer, if you're not familiar with processor instruction set, then you can always go with embedded C program, because you do not have to learn instruction set thoroughly. So would be better if you're changing the controllers. for you people, especially embedded C is very much useful, because each semester you learn different processors, different controller. Okay, so that's what you have here. The advantages. Finally, the advantages of the high level language. So reduce development time, developer independency, and portability. So reduce development time, it is definite because it requires less time. Developer independency, because you know, independently you can also, if the firmware is given to you, you can also understand, and you can also slightly try to modify the firmware given. And also it is portable. Reason, the embedded C is generally used worldwide, so you can use the same program, and you can put it in some other platforms, but you may have to change the device header file. Device header file needs to be changed sometimes if the targets are different. Then definitely you can write a firmware. So for basically writing a firmware, this is actually the accepted language. Okay. Probably for the time being we will stop a while, and next session we will continue how to mix assembly level language and a high level language and its advantages.